All right, so I always start with when I talk about binary numbers is I talk about basically you have two digits, 0 and 1 in binary numbers. And so I want to show you how you go about counting in binary. So here's my little gizmo, and you can see this in class as well. If you look at the big television, you'll be able to see this. I was hoping to use the iPad to project, but we don't have our Apple TV set up yet, and it's hard otherwise. So right now, what the top display is telling you is the number in base 10, okay? Because we're humans and we're used to doing our math in base 10. Why do humans do math in base 10? Anybody know? Well, probably because most of us have 10 fingers, right? So we count on our fingers, and so that's probably why we use base 10. Would make sense. Now, my son, when he was born, he had 11 fingers, surprisingly. So he has to do all his math in base 11. It's really confusing. It is. He has trouble in math class because of that. But yeah, he's got 5 or 6 fingers on his right hand. So when he was 6 years old, he'd go, "I'm 6," just holding up one hand. It would freak people out. Okay, so right now, basically, I was saying that binary numbers only have two states, 1 or 0, but you could model that in lots of different ways. Like, for example, if you have a switch, right? The switch is either on or off. So here I have a little light. The switch is on. There's a little light. So that little light would represent a 1, right? Or if you switch it off, that represents a 0. Notice what happens to our display up on top when I do that. See, this one light being on translates to the number 1 up on top in base 10. So base 10's up here, base 2's down here at the bottom. No people showing up. Okay. All right. So so the number 0, if you were going to write it in base 2 or binary, base 2 and binary mean the same thing, right? Is you would write 0, 0, 0, 0, because none of the lights are on. So if a light being on is a 1, then the light being off is a 0. So you put 4 zeros in a row. And then say I add 1 to that. Okay. So now that's 0, 0, 0, 1 is equivalent to 1 in base 10. Okay. Now I'm going to add 1 more to this column, right? I'm going to add 1 to 1. What's 1 plus 1? 2, yeah. But the problem is this is base 2, and we don't have a number 2 in base 2. All we have is zeros and ones, right? So what we have to do is we have to put in a 0 and carry the 1. Okay, just like we have to do in base 10 when we get to 9. We've got digits, single digits from 0 to 9, but as soon as you get to 9 and you add 1 to 9, you've got to put a 0 and carry the 1. Well, that's what I just did. I put in a 0 and I carried the 1. So 0, 0, 1, 0 in base 2 or binary is equivalent to 2 in base 10. Does that look like 2 on your screen, or does that look like 5? I think up there it looks like the number 5, but if you look at it in the classroom, it's the number 2. I think when you look at it at home, it flips it around. But so I'll hold it up for everyone in class, right? That's the number 2. 1, 0 in base 2 is 2 in base 10. And we can see that on our little device here. Okay. So now I'm going to add 1 more. I'm just counting. How do you count? Well, you just add 1 to the previous number, and then you get the next number. So that doesn't change. That works in any base. So I'm going to add another 1 here. And I get number 3. Because you take the 2, this is the 2's column, and this is the 1's column. So 2 plus 1 is, well, 3, right? And that's what it shows up on the top of the display. So people on their phones, if you could get off your phones and actually pay attention, because this is you're going to be quizzed on this near the end of class. So if you're not watching, then you're going to be missing out. Okay. All right. So here's the number 3, and again, that's the 2's column. That's the 1's column. You add them together, and you get the number 3. Well, how do you get the number 4? Well, if we add 1 here in the 1's column, Well, that would make it 2, and we can't, so we have to carry the 1. So we add 1 here. Well, there's already a 1 there, so 1 plus 1 is, well, that's 2 again, and we can't write the number 2 in base 10 because, or base 2, because we don't have that digit. So we have to carry it here. So it actually goes there, and then these 2 shut off. Just like it would in base 10 if you had 99. You know, if you had added 1 to 99, you'd have to carry that 1 across. So that's what we just did. So this is the 4's column. 0, 1, 0, 0 in base 2 is 4 in base 10. Okay. And then if I add 1 more, that's 5. If I add 1 more, I carry the 1 over to here. That's 6. So 0, 1, 1, 0 is 6. 0, 1, 1, 1, that's 7. All these are filled up now. If we add 1 here, we're going to have to carry that 1 all the way over to here and then 0 all these out. So I'll do that. Now we're at 8. Okay. So this is the 1's column. This is the 2's column. That's the 4's column. That's the 8's column. Okay. Notice that every time we go to the next column, we just multiply by 2. So that's 1, that's 2, that's 4, that's 8. If this was a bigger machine, it could go on as long as you need to represent that number. Any number you can represent in base 2, you can represent in base 10. Okay, so we have 8. We add 1 to 8, we get 9. And I shut this one off, turn this one on, we get 10. We add 1 again, that's 11. And then add 1 more, we get 12, 13, 14, 13, 14, 15. Then we have a problem. Our problem is all our lights are lit up. If we add 1 more, we need another switch over here on this side, right? To get 16, right? So we've run out of switches. So with 4 bits, okay, we haven't used that term yet. Bits, what's a bit? It's a binary digit. It's either a 0 or 1. So instead of just saying binary digit, a lot of people get tired of saying that. So they just call it a bit. Okay, binary digit is just a contraction of the word binary digit. All right. So now I'm going to put it in automatic mode. This is my other ideas. I wanted to show you how to count. And what they programmed the Arduino to do is just to show these numbers. Now we're going to actually build this with Arduino kits and have it count in binary, just like this is going to do right now. Except we won't have the fancy screen, but let's try it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, back to 0. 1, 2. See that pattern? It's an interesting pattern, okay? It doesn't seem to make a lot of sense. But if you look at it from a point of view of place value, this is 1, this is 2, this is 4, this is 8, and the pattern starts to make sense a little bit, or hopefully it does. Okay. Now, there's also other patterns that you may not be seeing, but as it's counting here, I would say watch this first column right here. What do you notice about that? Every time it counts, what happens to that light? Every time you add 1, well, it changes every time. It's on and it's off, then it's on and it's off. So every 1 time it changes its state from either a 0 to a 1 or a 1 to a 0. What about the second column? What do you notice? 1, 2, 1, 2, 1, 2. See how it changes every 2 times? Okay. So as you add 1, that second column is going to change every 2 times. Look at the 4's column. Same pattern. 1, 2, 3, 4, off. 2, 3, 4, on. So the value of that column, the place value of that column, also defines how often it turns on and off when you count. That's the 4th column. It changes every 4 times. 8th column the same way. Let's look at the 8th column. We'll wait till it changes. 1, 2, 3, 4, 5, 6, 7, 8, off. 2, 3, 4. See how that works? Okay. So when you do math inside of a computer, you type in an equation or you're using a spreadsheet, a lot of people think that the computer does all their math in base 10, but it doesn't do math at all in base 10. What it does is it takes the numbers that are in base 10 and it converts it to base 2, binary, does the math in binary, and then converts it back to base 10 to show to us humans, because that's what we use. We use base 10. But the computer doesn't think in base 10. It only thinks in base 2. Now, if you want to represent a relatively large number like 1,000, you're going to need a lot more digits than just 4. The largest number we can show with 4 bits is 15. But if you just keep adding bits to the end of it or to the top of it, you can make numbers larger and larger and larger. Like, what's the biggest number you can represent in 8 bits? Does anyone know? Well, you can just do the equation 2 to the 8th and it would tell you. Well, what is 2 to the 8th? Does somebody have a calculator? Or is it 256 or is it 512? 256? Yeah, so the largest number with 8, say we had another box and it was connected. With 8 bits, we could show numbers up to 256. Okay. If you add another bit, that's 512. If you add one more, that's 1024. If you add one more, that's 2048. You add one more, 4096. You add one more, that's 8000. You know, it goes on and on and on. Why do I know my powers of 2 so well? 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048. It's because I'm a computer person. I'm a computer scientist, and so I deal with these numbers constantly, always in base 2. If you're going to be programming at the lowest level of the computer, you really need to have your powers of 2 memorized, because you use that all the time when you're doing any kind of low-level math or any kind of computation inside of a computer, right? So here, perhaps your whole life you've been thinking your computer's worked in base 10, but it doesn't. It works all in base 2. It's either on or off. In fact, your computer is just a bunch of switches. That's all it is. Little silicon switches that can turn on and off in different patterns. And by using those different patterns, we're able to make the computer do amazing things. But realize it only has 2 digits to work with, a 1 and a 0. That's all. So it's pretty incredible. With just those 2 numbers, you can do everything a computer does with just zeros and ones. That's pretty cool. All right, so let's go. I'm going to share my screen here. I like my little Gizmo. Something I came up with a long time ago and been wanting to build. And I need to thank the folks out at George Fox for building it for me. And they made it, and they made it out of Arduino, the thing we're working on right now in class in our kits. It's the same Arduino. If you actually open it up and look at it, there it is. It's an old school blue Arduino Uno, the same board that we have in our kits. So we're going to learn how to code this. We're actually going to code this up and have our Arduinos light up our 4 lights. You remember that first circuit we did with the 4 lights? Well, we're going to make those 4 lights into one of these that counts in binary. So people still showing up. All right, let me let more folks in. All right, check the chat. All right, so base 2 we described. I showed you how to count base 2. It's kind of weird. Okay, it looks kind of strange, but it makes sense if you recognize the patterns. It's all based on patterns. And so what we're going to do is we're going to take that first circuit and we're going to see what we need to do to control that first light or that 4th light in Tinkercad. And then we're going to see what we need to do to change the program so that we turn our little 4 light program or circuit into a binary counter, just like this box. except we won't have the base 10 screen, but we'll have the base 2 screens. We can use lights and positions to represent numbers, and we can do that visually. So yeah, 255. So thanks, Ryan. All right. I like how you said 255 and not 256. In programmers and computer stuff in general, we always start counting at 0. Most normal humans start counting at 1, but on a computer, all the lights being off or all the digits being 0, well, that's 0. And so we have 256 numbers if it had 8 bits, but they're numbered from 0 to 255 because we start at 0. Okay. All right, let's go into Tinkercad and take a look at our 4-light thing. Tinkercad. And I'm going to go to my circuits, I think. I'm looking for my 4 lights. Oh, I have a second page. That's why I can't see them, because I did all these earlier. Yeah, so here's this one here. I worked on it a few months ago, but what I've set up is our 4 lights like we built inside of our Tinkercad setup, right? We've done this one. I'm going to take a look at my code to see if my code has all the necessary stuff in it. It looks like it does. Okay. Okay, so we're going to look to see how do we control that 4th light. If I actually run this, if I run the simulation, you can do this with yours at home. The blue light comes on for a while, then the green light, yellow light, and the red light. But again, it's not counting. It's just showing the different lights, making sure they work. Each light stays on a different amount of time. We want the lights to maybe change every second, like a clock. In fact, I have a binary clock. I'm not sure exactly where it is. It might be in the closet there, but I needed to show it to you. It shows you the time, but it's all in binary. And it makes my wife kind of angry at home when I have it at home. She goes, "What time is it?" And I go, "It's right there on the clock." Of course, it's all in binary, and she struggles with binary sometimes. And so just tell me what time it is, she says. Okay, so we want to turn these 4 lights into binary digits. So what I've done is I've taken it and I've rotated it a little bit and put it in so that this is the 1s column, this is the 2s column, this is the 4s column, this is the 8s column. Another way you can look at this is you can look at it like this is 2 to the 0, 2 to the 1st, 2 squared, 2 cubed, right? 2 cubed is 8, 2 squared is 4, 2 to the 1st is 2, and 2 raised to the 0 power. I always find that kind of weird. Why is something raised to the 0 power? Well, it's 1. It's not 0. Okay. So that's another way you can remember the values. You just think of whatever base you're in, and then you say that's 2 to the 0, 2 to the, if it was base 8, this would be 8 to the 0, 8 to the 1st, 8 squared, 8 cubed. So now we want to change our program to make this work. Now, how would you set this up on your actual Arduino, right? Well, we don't have a soldering iron in our kit. We wouldn't be able to solder these wires to the resistors or to the LEDs. Luckily, though, right next to our Arduino is a breadboard. So what I'm going to do, and I was hoping that we could try this today, is to get out your kits, and we're going to actually build this same circuit, but we're going to build it with a breadboard this time. Okay, so I'm going to go in here, and I'm going to grab a breadboard and pull this on, and I'm going to rotate it. Oops. And I'm not sure on my Arduino. Let's see, how's it? I want to orient it exactly the same. So I think our breadboard is over on this side. Oops. I'm just going to drag it over there. So our little Arduino kit has that set up this way. Now, so what I would think we do is first we'll model this using Tinkercad, and then we'll actually build it using what we model. That might be a good way to do it. All right, so here we have this ground wire, right? It's coming out of ground. I'm going to zoom in a bit so we can see a little bit better. And we're just going right to this negative node. Maybe we should take it from these outputs, right? Let's just go backwards, I guess. So I'm going to take this and I'm going to delete it. And instead of plugging into our light system, I'm going to just plug it into our negative power rail on our breadboard. And then I'm going to change its color to black because typically we use the color black to represent ground. Now, all these other connections, now that this power rail is going to ground, we can connect all of these to ground, and it will get to the ground that's inside the Arduino. So I'm going to move these LEDs next. First, I'm going to delete some wires. So the wires look really ugly when you move stuff. So this will be our 8s column. So maybe maybe I'll do this. What's the best way to model this? I want it to be in the same orientation, but I have to be careful here on how I do that. I guess I can't. I can't do this with the breadboard rotated this way. So I'm going to try rotating the other way and see. Yeah, let's do that. Because what that will allow me to do I like straight lines, so I take the time to put in these little elbows. All I'm doing is double clicking and trying to straighten out the lines like that. Okay. And then I'm just going to take my light and I'm going to rotate it around. I like being right side up. And we'll put it in maybe these 2 rows right there. So I'm just moving my lights over. We're going to use the same components, but instead of wires, we're going to rely on our breadboard to okay, so there's our 4s column. We'll put those pretty close to each other. It's going to get a little crowded, so maybe there. We'll start it on the other side. Okay, so we'll crowd it up. So yeah, I'm just deleting the wires because we don't need them anymore. We have our breadboard. Flip this around. And then finally the red one. If you remember, when we're talking about breadboards, we learn how they're connected. And so each of these parts of the LED, each of the wires coming out of the LED get their own row, which is what we want. That allows us to treat them independently because we're going to need to do that. Now, we need these resistors to be connected to our lights. It's somewhere in the circuit. Doesn't matter where you put the resistor, before or after the LED. And the answer is it doesn't matter. You can put it before, you can put it after. It's still going to slow down the current. So what I'm going to do is off of the short leg, oops, I didn't do my spacing right. I'm going to scooch these up just 1 slot because I need to put my my resistors there. And I'm going to connect them. I guess I have to scoot them up too because these resistors are a little bit taller. So again, it doesn't matter where in the row I connect the LED, but now I can connect this directly to the negative power rail. I'm trying to avoid having to use any wires. I'm just using the components. So I'm taking the short leg, which is this one, not the one that looks like it's bent, and I'm connecting that to the negative power rail. So the energy is going to flow through this row through the resistor into the ground and then over here. And we'll do the same thing with all the other short legs of our LEDs. All right. Now, where do the long legs come from? Well, this is where we have to connect these connectors over here. And so this might get a little bit ugly, but what I'm going to do is I'm going to start with line 0. I can line it up. And I want to go right there. And maybe I make that wire red so it matches the light color. So I know that's our red one. Okay. And then for line 1, well, line 1 is our yellow light, right? So maybe I use the yellow wire. And I'll drag it out. Trying to make it look nice. Engineers always try to make it look nice, even though it's not entirely necessary. You're engineers, right? And all I'm doing is taking the ports, 0, 1, 2, 3, into the long leg of the LED. Oh, I got to change my color here. I'm going to change that to green. Slowly building my circuit. And then finally the blue wire. So I'll switch to blue. And it looks somewhat professional. Straighten out the legs. All right. Now in theory, this never works, but in theory, this is the exact same circuit, right, that we had before. So the expectation is the blue light will come on, then the green light, then the yellow light, then the red light, because we haven't changed the program any. All we've done is we've added a breadboard so that we don't have to solder. I'm going to run the code and see if it still works. Yeah, there's the blue light. There's the green light. There's the yellow light and the red light. See that? So by including our breadboard in the circuit, now we can use a lot less wires and we don't have to solder anything. All right, so that's interesting. But now we want to get this thing to count in binary. Right now it's just blinking lights, right, from left to right. Be nice if we could actually count in binary, just like our little Gizmo thing here does. I'm going to go get that program. I'm going to stop this simulation, and we're going to replace the code. And we'll take a look at the code, and I'm going to try to keep it simple. So I'm going to go back. Let's go back there. What I'm looking for is a binary counter that's actually working. I think this one does. So I'm going to look at the code at that one and see if that one's been modified. Probably should have hunted this down before class started, but look at the code and see. Yeah, this is the right code. It says binary counter. With 4 LEDs, we can display binary numbers from 0 to 15. We saw that. I'm going to grab all of that code, and then I'm going to take it, copy that, and then go back to where we were. We're on page 2. And the one we were working on was, where'd it go? Now it's probably actually on the previous page. Since I changed it, yeah, there it is. And what I'm going to do is I'm going to replace the code that was already in there from our 4-wire experiment. I'm going to replace it with this binary counting code that I wrote. Did I write this? I'm trying to remember. Yeah, I found this online. It's actually pretty well done because it's really small. First thing you do is you just shut all the lights off, and then you just add one to the count and display that number, and then you wait about a half a second. So this is going to count not every second, but every half second. How do I know it's a half second? Because the delay here says 500. Well, that's in milliseconds. And remember, there's 1,000 milliseconds in a second. So if I say 500 milliseconds, that's half a second. Let's try it now and we'll see it work. There's 1, 2, 3, 4. It's going fast. 9, 10, 11, 12, 13, 14, 15, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 1. Right? We're not 16, but we get to 15, then we go to 0, right? We start counting at 0. We don't start counting at 1. But you see that pattern. See that pattern's repeating that stuff. That same pattern that we saw on our binary demonstration box, we now have working in our own Arduino. So what I'm asking everyone to do today is take their kits and build this circuit using this code, okay? And this circuit, I want you to build it out of your actual kit and see if we can build this binary counter similar to what the George Fox engineering students did for me just a couple months ago. I was really excited about getting this box, and it was the first day of classes that we had here at Southwidge at the beginning since the pandemic started, right? So the next day they were going to be opening up schools. You know, Mr. Nieslanik, our principal, drove all the way down there to see me get awarded this Gizmo, even though he was super busy. He took the time to drive down to Newburgh and help and take and kind of participate in the ceremony when they gave this to me. My nephew is going to be going to George Fox next year. He's not studying engineering; he's studying pre-med. But so I'll have a connection there. He's going to be living in our house, so that's going to be nice to have another young fella at the house. It should be fun. So give this a try. Try building this. The code is here. I will post this code online in our Canvas once we get there. But what I'd like you to work on today is just build the circuit. And you could try, we're going to learn tomorrow how to get it so that we can use our Chromebooks to code or to program our Arduinos. But that's going to take a little time. I'm going to make a little video of that before class tomorrow, so I don't have to do that in class. We can do that beforehand. And then you can use your Chromebook to program your Arduinos. And you can write this program plus any other Arduino program you want to try. We'll be able to do that as well. So that's the plan. Give this a try, see if you can build the circuit. And for real, and then we'll do some real coding in it and get it to count in binary. Any questions before we go today?